All right. Prerequisite stuff. First lesson we have here is on real numbers. Again, the majority of what we're doing in these prerequisite lessons are things that you guys should know very, very well by now and probably do not even need to look at these video lessons. But in this first lesson on real numbers, we're going to be looking at representing real numbers in a couple different ways: inequalities, intervals, number lines, things like that. We're going to be looking at order and interval notation, basic properties of algebra, so distributed property, commutative property, things like that. Basic exponent properties, and then some scientific notation stuff. And again, really the whole idea behind all these prerequisite things that these are fundamental skills that are going to be needed for us throughout the whole year, that I need to know that you can communicate a set of numbers using interval notation. From the book, the objective is students will be able to convert between decimals and fractions, write inequalities, apply the basic properties of algebra, and work with exponents and scientific notation. So, to kind of get started in this, we need to remember what a real number is. A real number is something that you can kind of point your finger to on a number line, which means there's a whole bunch of different types of real numbers. We have the most basic of those real numbers. They're called natural numbers. Sometimes you'll hear them also be referred to as counting numbers. That is the furthest one in here. You also sometimes hear these being called counting. After you include 0, it is called a whole number. After that, we start getting into negatives and positives. Those are called integers. Rational numbers are anything that can be written as a fraction. And then we have, in general, real numbers. Well, those real numbers can get broken into those rational numbers that can be written as a fraction, but there's also irrational numbers, which are the ones that cannot be written as a fraction. And then we're not going to talk too much about complex numbers right now, but remember we learned that last year there's also things beyond just these real numbers. Those imaginary numbers, those square roots of negatives, and that's what produces a complex number. So really for this lesson, we're looking at just the real piece of this. And we're going to talk a little bit about how you communicate a set of numbers. A couple different ways of communicating sets of numbers. If we have a discrete set, we use braces. So I'm just going to kind of read, this is just taken out of the book, but it's again all prerequisite stuff. We use braces, which are like those squiggly brackets, to enclose elements or objects of a set. The rational numbers are another important subset of the real numbers. A rational number is any number that can be written in the quotient of a over b of two integers. We kind of already said that. Really, a rational number is just a fraction. And we can use set builder notation to find the rational numbers. So they use set builder notation here. We will not use set builder notation all that often. That's something that's just kind of redundant. But here you can see that they're saying that a rational number is any number a and b such that we're looking at the number a over b, where a and b are both integers and b is not equal to 0. These symbols are read as a set of all a over b such that a and b are integers and b is not equal to 0. The decimal form of a rational number terminates, for example, like if I had 7/4, that is 1.75, or it has an infinitely repeating decimal, something like 4 over 11. We get that 0.363636, and we write that bar over top of the 36. The bar over the 36 indicates that the block of digits that repeats. A real number is irrational if it's not rational, which we already mentioned. That means it cannot be written as a fraction. The decimal form of an irrational number is infinitely non-repeating. So for example, square root of 3 in pi, pi goes on forever and ever and ever without a pattern being established. A real number can be approximated by giving a few of its digits. Sometimes we can find the decimal form of a rational number with calculators, but not very often. Generally speaking, and this is going to come up a lot, we always will round to 3 decimal places. That is an AP standard. Just so you guys have that in the back of your mind. So first question says determine the decimal form of 1/16, 55/27, and 1/17. And then you guys are going to do that a couple times as well. So 1/16 you probably can recognize as a pretty decent fraction, but if you don't know that off the top of your head, type in 1/16 into your calculator, 1 divided by 16. We end up getting 0.0625. Like I said earlier, generally speaking, we round to 3 decimal places, but because I know that these are rational numbers, it might be beneficial for me to record a couple more decimal places so I can see that pattern or that termination. So I'm going to say 1/16 is equal to 0.0625. That is an exact value. It is not an approximation. It is not rounding. It's nothing like that. 55 over 27. Again, I can tell that this is a rational number, which means I'm going to be having a terminating decimal, or I'm going to have something that repeats. And 55 divided by 27 in my calculator to help me out here. 0.037037, and I can see that repeating pattern. So I'm going to go ahead and say that this is exactly equal to 2.037. That bar has to go over the top, the 0, the 3, and the 7, because that's what's making, or that's the repeating part. 1/17, same thing. Type in 1 divided by 17 in my calculator. I'm not sure what this one is off the top of my head. And I get 0.0588235394. Now, as I'm taking a look at this, I don't really see where it's repeating. 058, I don't see a 058 anywhere else, which means I can't really write this in a great way. I don't see the repeating pattern. This one might be one that I just approximate to 3 decimal places. If I were to do that, this would approximate to 0.059. And again, there is going to be, if I were to expand this out far enough, this would either terminate or this would have a repeating pattern. It's just really hard for me to see in the calculator because the calculator gives me only a certain amount of places here. So I'm just going to make a little note. This will eventually terminate or repeat. I just don't know which one because I only get so many decimal places on my calculator. What I'm going to ask you guys to do right now is you're going to do the same exact thing. You're going to pause the video real quick and you're going to give me the decimal version of these 3. If you can't see where the repeating occurs based off what the calculator has, it's no big deal. What you would end up doing is you would just truncate it to 3 decimal places. So pause it, give it a try. All right. And actually all 3 of these you can see where they terminate or where they start repeating. 1/4 you should know is 0.25. 3/7. If you look just a little ways down, you're going to see that the repeating portion is a 0.428571. And the same thing with 5/13, so you'll be able to tell where it repeats. I just forgot my bar over top. It repeats the 0.384615 repeats over and over and over again. Okay. So again, real numbers just mean we can plop it on the number line. We can kind of exactly tell where whole numbers are because that's how we write the number line. We can tell exactly where any integer is because that's how we write the number line. When we start getting into rational numbers where we have to get either a decimal or a decimal approximation, we just kind of have to guess where that is. But I'm just going to read a little bit here out of the book. It says the real numbers and the points of the line, the real numbers and the points of a line can be matched 1-to-1 from a real number line. We start with a horizontal line that matches real number 0 with point 0, the origin, or the origin. Positive numbers are assigned to the right of the origin, negative numbers are assigned to the left. Again, this is nothing new for you. Every real number corresponds to one and only one point on the real number line, and every point on a real number line corresponds to one and only one real number. Between every pair of real numbers on the number line, there are infinitely many more real numbers. That just basically means I can keep on taking my decimal and making it smaller and smaller and smaller and smaller. The number associated with the point is the coordinate of the point, as long as the context is clear. We will follow the standard convention of using the real number for both the name and the point and the coordinate. So just a little bit more here with basic number stuff. Order and interval notation. This actually might be a great place to stop because we're done. No, let's go a little bit further. We'll finish up with number lines. It says the set of real numbers is ordered. This means that we can always use inequalities to compare any 2 real numbers that are not equal to and say that one is less than or one is greater than. That's something, again, that makes a lot of sense for you. If I'm comparing 3 and 4, I know that 3 is less than 4. That's all that this idea of ordered means, is that there's one number that's more than one number that's less. And that's really all this next box says. It says let A and B be any real numbers. That means that we have A is greater than B, A is less than B, A is greater than or equal to B, A is less than or equal to B. They're all comparisons. Okay. Geometrically, A is greater than B means that A is to the right of B on the number line, and vice versa. If A was less than B, that means it would be to the left. For example, 7 is greater than 3 implies that 7 is to the right of 3 on the number line. Note that a is greater than 0 means that a minus 0, or simply a, is positive, and that a is less than 0 is that a is negative. That makes sense. A is greater than 0, that just means we have a positive number. If I have a is less than 0, that means it's a negative. Okay? Don't really worry about the trichotomy property, but it does make sense if you stop and think about it. That means if I'm comparing three numbers, that either means that they're the same number, one's less than, or one's more than, greater than. That's all that means. Again, something super, super basic. You probably just never heard it called by name before. Inequalities can be used to specify intervals or real numbers, as illustrated in example 2, which we'll be doing here in a second. And intervals and interval notations is going to be one of the most common ways we communicate a set of numbers. It says explain the meaning of and graph the interval of real numbers for the inequality. So I'm actually going to do this three separate ways. I'm going to explain it, I'm going to write it on a number line, and I'm going to give the interval notation as well. So here we go. It says x is less than 3, so that means all numbers less than 3. On a number line, that would look like this. There'd be a 3 on the number line. 4 is to the right, 2 is to the left. I would have an open dot because I'm not including the 3 and I'd be shaded to the left. If I were to record that using interval notation, I'm shaded all the way to the left and up to 3. Now, hopefully we remember what interval notation is. That's something that if you had 8th grade Algebra 1, you might not have seen that much in Algebra 1, but you did see it in Algebra 2. B, same exact idea here, except for now my inequality is different. That has, let's see here, we have all numbers greater than -1 and less than or equal to 4. On the number line, -1, 4, I would have a closed dot on the 4, I would open dot on the 1, shaded in between. In interval notation, parentheses, -1, comma, 4, bracket. Remember, the parentheses means I'm not including the endpoint, the bracket means I am including the endpoint. I'm going to ask you right now to pause and try to do this again for this next inequality, x is greater than or equal to -4. All right, here you go. All numbers greater than or equal to -4. On the number line, it'd be a closed dot, -4 shaded to the right. And as an interval, it'd be a bracket on the -4, comma, infinity with a parentheses. That's going from an inequality to words and interval notation. We're also going to go the opposite direction, where now we're given an explanation in words. We're going to write it as an inequality. We're going to draw a graph, and we're going to write it as an interval. So here we go. A says the real numbers between -4 and -5. Well, in between -4 and -5, I would have -4 is less than x, which is less than -0.5. On a number line, I would have a -4, I would have a -0.5. I'm not including either one of those endpoints, and I'm shaded in between, which means as an interval, it would be parentheses, -4, comma, -0.5, parentheses. D. Pick a new color in here. The real number is greater than or equal to 0. So that would mean I would have x is greater than or equal to 0. On the number line, I would have my 0 with a closed dot shaded to the right. And an interval notation, that would mean that I would have a bracket, 0, comma, infinity, parentheses. Again, your turn to practice this skill here really quick. You are going to do the same exact thing with the phrase, the real number is less than 2. All right, that would mean you'd have the inequality x is less than 2. You'd have an open dot on the 2 shaded to the left, and as an interval, it'd be from -infinity up to 2 with a parentheses on the -infinity and parentheses on the 2. We'll break here when we get through all the interval stuff. So, kind of as a recap what we just got done saying about interval notation, as shown in the last example, inequalities define intervals on a real number line. We oftentimes use the brackets here, 2 to 5, to denote the bounded interval determined by 2 is less than or equal to x, which is less than or equal to 5. This interval is closed because it contains its endpoints 2 and 5. There are 4 types of bounded intervals. And as you take a look at this, you can tell, and just look at these things, that we have a difference between a bracket and a parentheses. to generalize this, brackets, and let's just get back to a black marker here. Brackets are the same thing as a closed dot, which is the same thing as having the or equal to. Whereas parentheses are the same thing as open dots, which is the same thing as no or equal to. And that means that this is including and this is excluding. And you can see how an interval is closed when I'm including both those endpoints. It's open when I'm excluding both those endpoints, and it's half open / closed when I have one of those included and one of those excluded. We use interval notation negative infinity to infinity to represent the entire set of real numbers. The symbols negative infinity and positive infinity allow us to use interval notation for unbound intervals. These symbols are not real numbers. So sometimes if I have a situation where I'm talking about every single real number, I go from negative infinity to positive infinity. You'll also see that notated as the capital R, which just represents all real numbers. Those are two synonymous ways of saying the same thing. And now if I'm not looking at an interval that's got a top and a bottom point, I could just be looking at a bottom or top point and going up. So the interval of real numbers for the inequality x is less than 2 can be written as the unbound interval from negative infinity up to 2. This interval is open because it does not contain the endpoint 2. In addition to negative infinity to positive infinity, there are 4 types of unbound intervals. And again, that just means we go up forever to positive infinity or negative infinity. As you're seeing, we saw earlier, closed dot is a bracket, which is less than sign, less than or equal to sign, greater than or equal to sign. Open dot is a parentheses, which is a less than or greater than sign without the or equal to. So now, instead of taking algebra and taking inequalities and going in intervals and number lines, we're just going to kind of put it all together. So you can convert interval notation to inequality notation or vice versa, state whether the interval is bounded or unbounded, and open or closed. Graph the interval and identify its endpoints. So I'm going to do 3 here with you. After we're done doing these 3, you're going to try 2 on your own, and that'll be it for intervals and inequalities. First one, I'm going to take this bracket -6, 3, I'm going to turn it into an inequality right away. I have x is less than 3 and greater than or equal to -6. On a number line, that would mean I would have a -6 on the left, a 3 on the right, a closed dot on the -6, an open dot on the 3, shaded in between. I also need to identify if this is bounded or unbounded and if it is open or closed. So this is definitely bounded because I have 2 endpoints, but only one of those endpoints is being included, which means this is half open, half closed. And it does also ask me graph the interval and identify its endpoints. So I'm also going to identify the endpoints. The endpoints in this case are -6 and 3. Do the same thing for the next question. I have from negative infinity up to -1, which means I have x is less than -1. On the number line, there's -1. I would have an open dot, -2, excuse me. I would have an open dot shaded to the left. This, because I don't have a top and a bottom, this is unbounded. And because it's unbounded, I just look at if I'm including the endpoint or not. In this case, I am not including it, which means this is an open interval. And I only have one endpoint here. And the one endpoint is that number -1. And then last but not least, I was giving it as an inequality, compound inequality. Now I need to write it as an interval. I have a bracket, -2, 3 bracket on the number line. -2, 3, I would have a closed dot at both of these, shaded in between. In this case, it's bounded because I have a top and a bottom. I'm looking at the top and the bottom of both closed dots. which means this is not an open interval, this is a closed interval. And not only that, I need to identify my endpoints. And my two endpoints are -2 and 3. All right, your turn. What you're going to do is you're going to do the same exact thing here for the two expressions given directly below. X is greater than 3 and the interval from 5 to 11. All right, x is greater than 3 would be the interval from 3 to infinity. I would have it open dot in the 3 shaded to the right. This is unbounded because I only have one endpoint. It is open because I am not including the 3, and my endpoint, my singular endpoint is 3. The second one, I was given an interval, change it to an inequality, 5 is less than x and less than or equal to 11. On the number line, I would have an open dot in the 5, a closed dot in the 11, which means it's bounded. I have two endpoints. And it's half open because one of those endpoints is included, one is not. The endpoints are 5 and 11. So that's a really good place for us to break this lesson into a part. The whole first part here was just dealing with communicating sets of numbers, inequalities, intervals, number lines, stuff like that.